Hello everyone, you are welcome again for the second part of the probability theory. In this part, we talk more about a few concepts of probability, and as I said in the beginning, so it is just a fast review without going into details. In previous part, we mentioned about the probability or the conditional probability of x given y, and we said that it is probability of x and y divided by the probability of y, and we extended this further for the to Bayesian theorem, and we said that it is the same, that probability of x given y, we can say that it is probability of y given x times probability of x divided by probability of y. This actually could be also extended for not only for two random variables or two events, but it can be also extended in general. So we can say that probability, for example, of x given, let's say, y1, y2 is the same. So we can say that it is probability of y1, y2, and y2 joint probability given x. Okay, so you can just make the swapping for this times probability of x divided by probability of y1 and y2. Okay, and actually even this one could be extended further. So probability of y1 and y2 given x can be extended like probability of y1 given y2 and x and so on. So we can come later for this for more details, but now it is important to define the random variable. What is a random variable? Actually, random variable is a mapping between the events space to the real numbers line. So what that mean? We talked, for example, about tossing a coin. Assume that you toss a coin 2 times. Then the sample space in this case will be, we know that it is head, 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 tail, tail, head, and tail, tail. So this is the outcome of this experiment of tossing 2 coins. Of course, this is just a symbolic example which can be applied in many other applications. Now we have symbols. Actually, this is event 1, event 2, event 3, event 4. We can define from this experiment that we can make a map for this experiment. So we say that our random variable, for example x, is equal to number of heads appear or landed. In that case, our random variable becomes 2 for this one. This one will be 1, 1, and 0. Okay, now we can say that what is the probability that x equal to 2 if it is equally likely, because now we have 4 elements, and if they are equally likely, then the probability that x equal to 2 is equal to 1 over 4. And probability that x equal to 1 is, we have this one and this one. So we have 2 out of 4, so it is half. And probability that x equal to 0 is equal to also 1 over 4. And the summation now is the summation of probability of xi for, now we have, or x equal to, okay, we can say that x1, x2, x3, or we can say that it is x equal to I, okay, x equal to I, and for all I, this equal to, of course, 1. Yeah. So now this is called a random variable. So the random variable is the mapping process between the event space to the real number space, or real number line. Okay, so actually random variable x can be any number from minus infinity up to infinity, and this simplifies a lot the dealing with probability and with events. So it is much easier to deal with numbers than to deal with symbols. And this, for example, what is, if I asked you question, what is the probability that x square, for this example, x square plus 1 is less than or equal to, for example, let's say 1, or less than or equal to 2. Okay, just an example. What is the probability that x squared plus 1 less than or equal to 2, which means that it is a probability that x squared less than or equal to 2 minus 1 is 1. What is the probability that x squared is less than 1? Which means that, of course, x will be the less than or equal to a plus or minus 1. Okay, now if you look to this, we can solve such equation, because now we have mathematical equation for the random variable. So for this one, when x equal to 2, this will not be achieved because 2 square is 4. 1 square is equal to 1, so this half is included. Okay, and also 0 is included, so this probability equal to half plus 1 over 4. Okay, this was not possible if we are dealing with still with symbols. So dealing with numbers makes things much easier. So this is the main motivation for using random variable, that we start deal with numbers instead of like just events or symbols. Okay, and now we define the joint probability. Joint probability is simply that if we have more than one random variable, for example, assume that we have x1, x2, and x3 random variable, so we can say that the joint probability between them is probability of x1 and x2 and x3. So actually now we use the comma. When we were using events in event space, we use this the concept of union and intersection. Okay, so when we use, for example, like event e1 and event e2, because they are could be represented as sets, and now when we say that what is the and, so it is intersection, so it is e1 intersect e2, so it means that here it is and operation. But in when we deal with random variable, we use the comma, which means also and. So this is joint probability, so between x1 and x2 and x3. Okay, if you remember from session 1, if x1 and x2 and x3, all of them, they are independent, then the probability of joint probability for this, now we are dealing with discrete probabilities, so it becomes like probability of x1 times probability of x2 times probability of x3. Okay, if I asked you what if they are dependent, of course we have to use the conditional probability, so we need to know the interrelation between them. So we can, for example, express this as probability of x1 and x2 and x3. Okay, this equal to the probability, for example, of x1 given x2 x3 times probability of x2 and x3. Yeah, because this is the conditional probability that, as you can see from the previous session. Of course, we can also solve this one in the same way. So this one could be done like yes, because this probability of x2 and x3 is equal to probability of x2 given x3 times probability of x3. So you can substitute this here. So this will be probability of x1 given x2 x3 times probability of x2 given x3 times probability of x3. This could be like expanding in this way. Okay, Yes. What else? Um, we can also talk about probability mass function. As we said now, we want to put some model for the uncertainty. We need to put some model for the uncertainty. So assume that we have a certain experiment or certain process, okay, which generates, let's say, four possible events. So it can which could be represented by certain random variable. So we can say that it is x1 or x2 or x3 or x4. So this is the outcome. How is the distribution of this probability? So the probabilities in this case, because they are discrete now, so we can assume that this is, for example, what is the probability of x? This is x. We have only discrete situation, so we have x1 and x2 and x3 and x4. Okay, and this is the probability of x. So assume that this is the probability of x. Example, and this is b1 or b of x1, probability of x2, probability of x3, and probability of x4. Actually, this figure represents the uncertainty or modeling the uncertainty of this experiment. We know that the summation of probability of xi from I equal to 1 to 4 must be 1, because this is all possible outcomes from this experiment. This probability of x1, x2, x3, x4 is called probability mass function. Probability mass function. Okay, so we have this now for four probabilities. We can have actually any number of probabilities. Assume that we throw a coin, okay, and our random variable is the number required before we get the first head, and assume that the probability of head is equal to b, which means that the probability of tail, of course, will be 1 minus b, because we have only two events here. And now we throw the coin, and our random variable n is the number of tossing of this coin before we get the first head. Okay, so what is the probability that n equal to 1? A probability n equal to 1, it means that the first throwing of the coin we got head, which means that it is b, this one. What is the probability that n equal to 2? Probability n equal to 2 means that the first tossing was tail, and the second one was head, and both of them are independent, which means that we should multiply them. So it is the first one was tail, the second one was head. So it is 1 minus b times b. What is the probability that n equal to 3? It will be the same, 1 minus b square times b, because the first two throwing result tails, and the third one was head, and we can continue in this way. So in general, that probability that n equal to n small equal to 1 minus b of the power n minus 1 times b. Okay, now we can have this like this way. So we can start from n equal to 1 and 2 and so on. So we have these probabilities now going down in this way. So this is another shape of infinity, actually, probability mass function, because n can be up to infinity. Of course it will, after few iterations, becomes very close to 0, but still theoretically it continue to infinity. So this is probability mass function. The simplest form of probability mass function is known as Bernoulli distribution, where that it means that or it expresses the process of making certain process or certain experiment 2 times, and we have only 2 outcomes, which is b and 1 minus b. So if you have any event which or any experiment which gives only two outcomes. Okay, for example, x and y, or x1 and x2, and this with probability b, because it has only two outcomes, the other event will be 1 minus b. This is called Bernoulli distribution. Okay. Now, if we assume that the outcome which gives b, we give it a random variable x equal to 1, and the other one we give it like x equal to 0. Okay. Now, if we repeat this experiment n times, okay, and they are independent. We repeat this experiment n times, but they are independent. So then what will be the outcome? And we just add the result. So the output y will be the summation of xi from I equal to 1 up to n. So we repeat this experiment n times, in capital times, and then we got this xi. So once we get the outcome, for example a, we should add 1. If the outcome was b, we should add 0 here. Okay, now you can see for this experiment what is the possible values of y. The possible values of y is y equal to 0. 0 means that all outcomes are 0. So it means that if this is the event A and this is event B, then it means that all outcomes of this n outcomes, all of them, they will be. So we add only 0. 0 plus 0 plus 0. So the total will be 0. But y could be 1. And y can be 1 when only one of the outcomes were A. Okay, so in this case, if we have, for example, the outcome, assume that n equal to 3, okay, then when the y equal to 1, y equal to 1, if we have those outcomes a, b, b, then it will be 1. But also b, a, b, this equal to 1. And also b, b, a, this equal to 1. So we have three options actually. We have three options to get the summation equal to 1, and it can be 2, it can be 3, it can be up to what? Up to n, because if all of them were a, then the result will be n. So this will be the outcomes of this experiment. This could called binomial distribution. It is called binomial distribution, and the probability that y equal to n small, okay, out of n experiment or of n repetition, this gives us the n factorial divided by n small factorial, n minus n small factorial, okay, multiplied by, because we have y equal to n small, it means that the outcome A was n times, and every time is p, so it becomes p the power n. Okay, and what is the rest? The rest is n capital minus p, and it will be for the second event, so it will be 1 minus p of the power of n capital minus n small. Okay, what is this number? This number actually, it gives us the number of possible ways to get only, for example, the number n out of n capital. This is the possible ways. Okay, so for example, if what is the possible ways to get 1a out of 3 trials? So n capital equal to 3, so it becomes 3 factorial divided by n small is 1, so it is 1 factorial, times n capital minus n capital is 3, and n small is 1, so 3 minus 1 is equal to 2, so it becomes like times 2 factorial. And 3 factorial is 3 times 2 times 1, divided by 1 factorial is 1, divided by 2, so 2 cancels 2, and the result will be 3. And those are the 3 cases. Okay, so and for everyone, for example, for this, it will be b times 1 minus b square, and for this also b times 1 minus b square, and for this also b minus 1 minus b square. But we should multiply them by 3, because this will be this one or this one or this one, and all of them, they are mutually exclusive, which means that we can add them together directly. So this is called the binomial distribution, and this is another way of probability mass function. Okay. However, it is important to remember here that the probability distribution, or the probability, or the random variable, it can be also continuous. It is not necessary that the random variable is only discrete, so it can be also continuous. And in continuous case, for example, if we are interested in sorry, interested in temperature is continuous, and or the received signal voltage or magnitude, or it can be the pressure level, for example. Actually, many situations, the signals coming from, like, power grid, in the protection. So how will be the signal shape, and in the details of the signal shape, which is related to the frequencies and time, the transient in time, and so on. So we have actually many applications where the random variable could be represented as a continuous case. In the continuous case, we define what is known as a probability distribution or probability density function, which express the uncertainty in any random process, so or any random variable. For example, we have, if we have this probability density function, and assume that it is for this is the random variable x, and this from A to B. Okay, what this mean? When we have probability density function in this shape, it means that this random variable has any values between A to B. Okay, how many values in continuous case from A to B? Actually, we have infinity number of values it can be. For example, if A equal to 1 and B equal to 2, how many values between 1 and 2? Of course, we have infinity number of values. It can be 1, 1.001, and so on. So we have actually infinity number of values. It can be between 1 and 2. Okay. This values, because we have infinity number of values, in that case, what is the probability that you will get certain value? For example, if it is from 1 to 2, what is the probability? This is x, okay? What is the probability that x equal to 1.5? Okay, this probability of exactly 1.5 actually is equal to 0. Why it is it equals to 0? Because it is a single value. Why it is not 1.5001? It can be like that. When you say 1.5, it means that after this 5, we have infinity number of zeros. And to get exactly such number, look, now we talk about theoretical things. In the practical, we have always finite accuracy. We cannot go to infinity accuracy in the practical. Okay, we can go, for example, 8 numbers, we can go 16 number, 32 number, but at the end we have certain accuracy. Okay, but theoretically, the probability that x equal to 1.5 exactly is equal to 0, because now you need to divide this event by infinity number of possible events here, which means that it is 0. And this comes from what is known as measure theory. Okay, which is one of the foundations of probability theory, and this actually solved some problems in the formulation of the probability. Okay, and however, remember that probability that x are greater than or equal to 1.5 and less than or equal to 1.5 plus delta, where delta is any number greater than 0, any number, it can be even 0.0 or 100 this is not necessary that equal to 0. It depends, of course, where is it. Okay. So, but when we talk about a continuous case, the probability of achieve a single number in continuous case is equal to 0. Okay, now the probability in this, when we have this shape, we know that the uncertainty x, it can have any value between A and B, and they are equally likely. The possibility is equally likely. Okay. Um, One of the required condition for the probability density function, usually we represent the probability density function as f x of x. Some books they use different form. They use like our textbook. They use small b of x, and for mass probability mass function they use capital B. But in I do prefer actually in my courses to use function f of x instead of using b, and just keep b for the probability mass function for the discrete case, and using f of x for the continuous case to distinguish between them. Okay, so this is called the probability density function. Usually we put here x to, because sometimes we can have also joint distribution. For example, if you have f of let's say a and b, what this mean? What is the original random variable here? So we can put here x, for example, and y. We have some situation, we might have like x, y, z random variable, or even more. Okay, and then we have f a and b. So this can be confused sometimes, confuse students that what we mean, is it x and y or y and z or something. So we usually put it outside. Okay, this function. So if x capital is the represents the random variable. Okay, and then we have x small to represent the change in this random variable. Okay, so this is the this is called the probability density function. What is the probability to be, for example, between, let's say, x1 and x2? Actually, the probability here, or the conditional, the requirement here, is the total area under the probability density function from minus infinity to infinity for any probability density function. This must be 1. Okay, this must be 1 because actually it reflects the same concept of sample space. It is a sample space, but in continuous case. In continuous case. Okay, so this is important to remember, that the distribution must be or the total area under the distribution must be 1. Okay, now if we want to compute the probability for this random variable to be between x1 and x2, simply it will be the integration from x1 to x2 fx of x dx. That's all. Okay, and to make it more general, so if sometimes we need to know, for example, for any distribution, maybe we have such kind of distribution. Sorry. Okay, so assume that we have such kind of distribution. Yeah. So and we want to know what is the probability that to be x in this area, or and in this area, and in this area. Okay, so now we have like 3 periods that we want to know what is the distribution of this of the or the probability of this random variable to be in these periods. Okay, so if we call these periods like xi, which contains this period and this period and this period, so in general we say that the probability, okay, that x is part of this period, okay, in this period, this will be the integration for x belongs to that periods fx of x dx. So this is the general representation of any probability density function. Okay. What is the most important probability density function, or probability density function or probability distribution? The most famous one is known as normal distribution, which is given by this shape. This is very famous one, very well known one. There are different reasons for that, like the central limit theorem and so on. So this, it has mean mu, and it has variance, which is represented by sigma square. Okay, and this usually is given for a single random variable, is given like 1 divided by square root 2 sigma x square. Okay, 2 by sigma x square, sorry, 2 by sigma x square, multiplied by exponent of minus x minus, it is mean mu x, this is mu x, okay, square divided by 2 sigma x square. So this is known as the formula of the normal distribution. One of the characteristics of the normal distribution is that if we have a random variable y equal to x1 plus x2 plus x3 and so on, and all these x1 x2 are random variables with any probability density function, so we have summation of many independent random variable with any distribution, then the result of this summation will approach to be normal distribution, will approach normal distribution. Okay, this one, which means that it is very good model to represent when we have complex process, we have complex situation. For example, we have many interactions, random interactions, but depends on many different items. Okay, so it is usually it is good approximation when we approximate that result to be normal distribution, or in electrical engineering we call it Gaussian distribution. Yes, and now we can talk about the cumulative distribution function. It is usually is known as CDF, cumulative distribution function, and the CDF is given as the probability that x, random variable x, less than or equal to x0 or x dot. Okay, and this is called the CDF, which means that what is the probability that random variable x to be less than or equal to some specific value, and this will be given as for the continuous probability as the integration from minus infinity up to x0 fx of x dx. For the discrete case, for the probability mass function, it is given as the summation of probability of xi, where xi, for all xi less than or equal to x0. Okay, this is called the CDF. And in case of joint probability, so if we have like joint probability of x and y, for the probability density function x and y, we can actually find the distribution of x as if we like averaging over all values of y. It means that it is the integration from minus infinity to infinity fx and y, x and y, dy. This gives you f of x. Fx of x is the integration over all values of y, and the same can be done for y. So fy of y equal to of x and y with dx, and also it is the same for probability mass function. So if we have probability mass function for two like xi and yj, and if you take the summation, okay, over all yj, for all yj, this gives you probability of xi. Okay, so we can if we have joint probability between more than one random variable, we can see that the uncertainty in one random variable by averaging over all the other distributions or the probability or the random variables. Okay, and also, if we have like mathematical relation, for example, if we have y equal to function, some function in x, and x is a random variable, then of course y will be also a random variable. So if this is a random variable, this will be also a random variable. Okay, and in general, of course, and then if we know the distribution of x, how will be the distribution of y. Okay, this is also easy to find. Actually, if we represent this as like x and j of x, this is the function or the relation between x and y, and assume that it is given with some certain equation. Okay, and then we have also here the distribution of x, so this is fx of x, and assume that it has, for example, some distribution, and we are interested here to find, actually, this is because this is y and this is fy of y, and we are interested to find what is the distribution of y. What will be the distribution of y? Of course, this cannot be distribution in this shape. Okay, so it can be, for example, this way. Now, how to find that? It is a very straightforward and easy way that if we have like certain delta x, so if x has been changed from x1 to x2, so we call this as delta x. Okay, so delta x, what is the probability that it will be changed in this delta x? Of course, it is f of x times delta x at x equal to x1. Okay, so this gives you the probability that x will change from x1 to x2 within this period. Okay, so now if we change from let's say from x1 to x2, this is the probability that to be achieved. And if we make this up and we take this to the other side, so this actually this probability, because now when x changed from x1 to x2, it corresponding to changing from y1 to y2. However, these probabilities are the same, so this will be the same. This is fx of x. This should be the same as probability, that's the distribution of y, okay, times delta y when y equal to y1, assuming that this is y1. Okay, assuming that this is y1. Okay, now we are interested in this fy. We are looking for what is the distribution of y. Then the distribution of y in this case is equal to fx of x at x1, okay, and this delta x divided by delta y. Okay, and this will be at y1, and this will be, we can say that this is at y1, and this will be at x1. Okay, however, delta x and delta y, it might be not in the same direction. Okay, but we know that the distribution of y must be always positive. So delta x, delta y, it reflects how fast, or what is the interrelation of the changing of delta x to delta y. For this reason that we will put the absolute value to guarantee that we take only the magnitude of this changes, not the direction, because the direction can change the sign, which makes it negative, and we know that probability density function cannot be negative value. Okay, and in general, when delta x goes to 0, then we can have this. I just maybe take this off to write it here. We erase this part. Okay. Okay. Now, when delta x goes to 0, this could be represented as, in general way, fy of y equal to, okay, fx times dx over dy, absolute value. And here, because we want everything to be function in y, so what we do here, so if x of x, instead of x, we know that x equal to j inverse of y. So we put here like of a j inverse of y. Okay, so it will be like j inverse of y. So in general, this will be the result that we can find distribution of y base it on the distribution of x, given that the function is inversible or invertible. This will be that if y of y equal to f x of j inverse of y divided by d j of y with respect with x, okay, j of x, sorry, j of x with respect to x, and we take the magnitude, the absolute value for that. Okay, so that's all about finding the distribution. In case that for example, when the relation is given in two different values, for example, if y equal to x squared, now the inverse x equal to plus or minus square root of y. Okay, which means that when we take this one, we have to take them because this plus square root of y or minus square root of y, which means that it is or. And since they are mutually exclusive, cannot be in the same time plus square root of y and in the same time minus square root of y, there is no, they are disjoint events or disjoint random variables, and in that case we can take the summation in this case in this way. If the function is not monotonic, then we can make in general that we can take the summation, for example this as at y1, and then we take the summation f of x j inverse of y divided by the j of x divided by jx, and at y2, and so on. So you can take the summation in this case. So this is the conversion from related to this function. Of course, this could be also extended because this is one-to-one. This is memoryless relation, but also it can be relation with memory. And relation with memory, it means that differential equation. So in case that we have differential equation, which means that the relations are like changing with time, and in that case we should define the random process, not random variable, because now there's a process in time, like time series, and we can see how to convert that the distributions, and then we will have like a differential equation where we have also accumulation or distribution of the probability density function itself. So the probability density function becomes itself function in time. Okay, so this we can come later for that. Yes, so about the probability density function, we mentioned about the normal distribution. There is another very there are many actually famous and well-known distributions like exponential distribution, chi-square distribution. We have different kind of distributions, and they are given already in the online lectures related to the machine learning course, and they will be added to this part later. Okay. Now we come to another topic which is also very important, is the expectations. So what is the meaning of expectation? Expectation means that you are taking the average. Okay, you are taking the average. So when it is usually written as like E, expected value of a random variable. So when we put EX, it means that we are looking for the average value of X. When you write expected value of X squared, we are looking for the expected value of the square of random variable X. So if X is voltage or current, then this expected value of the voltage average, or the average of voltage or average of current, when you take X squared, it means that the power average, the normalized power average. Okay, you can take the expected value of X cube or whatever. So in general, we can say that it is expected value of F or maybe it is not good to use f, because if we use it for our random probability density function. So let us use any other function, for example j of x. So it means that the averaging of the mapping of x through the function j. So this is very general formula. So the expectation means averaging. Expectation means averaging. Okay. So and now when we say that what is the average value of x, the average value of x is equal to the integration, okay, from x fx of x dx, from minus infinity up to infinity. This is the general formula of finding the average value of x. It means that you multiply x by its probability density function dx. So it is like weighting integration, because it is weighted by fx of x. So you know that for the areas where fx of x is very small, it means that the probability can be very small to be x within it. Then the areas where fx is large, then the probability will be large. So in discrete case, if we have like random variable x, in discrete case, assume that x vector is x1, x2, up to xn in discrete case. So what is the average for this one? The average is also summation. It is the same idea. So it becomes xi times probability that x equal to xi from I equal to 1 up to n. So it is the same concept like this one, but this one for the continuous case and this one for the discrete case. Usually also for the expectation, for example, if we have more than one random variable, for example x times, we are looking for x times cosine y, for example, and x and y random variable, usually we should put here, we are averaging over what? So we can put, for example, x, expected value of x, or the expected value of x and y in the same time. So usually we can put the random variable name outside to distinguish that we are looking for the expectation for that random variable itself. Okay. So this is about the expectations. Usually the expectation of any deterministic number, for example, expectation of 5 equal to 5, it will not be changed. Okay. Also the expectation is linear process. So if you have expectation of x plus y, and both of them they are random variable, then this equal to expectation of x plus expectation of y. Okay. But expectation of x times y, this in general does not equal expectation of x times expectation of y, unless in very specific case when x and y are independent. So if x and y are independent, then it can be done. How to be computed if they are in general case? So in general case, expected value of x times y equal to expected value, okay, or sorry, this is equal to the integration, equal to the integration, double integration actually, because now we have two random variables, x and y. So now we have x and y. It will be x times y, fx and y of x and y dx dy from minus infinity to infinity and from minus infinity to infinity. Okay, so this is the way of finding the expectation of x times y in general. Okay, now if x and y they are independent, if x and y are independent, then f of x and y, it is the same as the probability case, okay, is equal to f of x times f of y, x and y. So this could be done in this way. Okay, now substitute this here, then it will be like double integration x y fx of x times fy of y dx dy. Okay, now they are separated, so it can be easily separated also in the integration. So it becomes integration of x dx times integration of y fy of y dy, and this will be the expected value of x times expected value of y, of x and y. So actually this is the case when x and y are independent. So when x and y are independent, then the expectation could be also separated in this way, but this will be only if x and y are independent. Okay, otherwise it is not possible to do that. Okay, and based on that we can define the covariance. The covariance element is that the covariance between two random variables x and y is equal to the expected value of x minus its mean mu x multiplied by y minus its mean, y minus its mu y. Okay, so now if they are independent, this could be also separated. It will be like expected value of x minus mu x, okay, times expected value of y minus mu y. This one is equal to, as we said, that expectation could be distributed inside, so it is linear operation. So it will be expected value of x, which is mu x, minus expected value of mu x, and mu x is not random variable, is like deterministic. So it becomes mu x minus mu x, which means that this is 0. 0 times 0 equal to 0. Then the covariance matrix for independent random variables, if x and y are independent, then the covariance between x and y is always equal to 0. If x and y, they are independent. Okay. Okay, what is the covariance of x and x? Covariance of x and x is actually nothing but expected value of x minus mu x square. And x minus mu x square is actually the variance. The expected value of x minus mu x square is the variance. So it is sigma x square. It is the variance. So, okay, this one. This is for independent case. This is for the independent case, and this is for the covariance Cx and x equal to the expected value of x minus mu x square, and this will be sigma x square. Okay, so in general, if you have let's say we have vector, okay, of possible random variables. So we assume that we have different random variables. All of them, they are continuous. So but we express them as x1, x2 up to xn. Okay, and now every element here is a continuous random variable, but they are like it in general way, so it can be dependent or independent. Now let us assume that they are dependent in general. So what is the covariance of this matrix? So what we will do here, we say that the covariance of this matrix can be computed in this way. So the covariance of x, okay, is equal to the expected value of, it becomes assume that x now is like a column vector. Okay, so it is transpose. It is a column vector. It means that it is x1, x2 up to xn. Okay, so it is n by 1. Okay, so it becomes like nx minus its mean. So here I will explain what this means also. It will be multiplied by x minus its mean transpose. Okay, so what this means? It means that mu x is also a vector. It is also column vector with mu1, mu2 up to mu n. Okay, so now when you take x minus mu x, it means that x1 minus mu1, x2 minus mu2, x3 minus mu3, and so on, multiplied by x minus mu x, but transpose. And this one, the dimension is n by 1, and this one will be 1 by n. So as we know from the linear algebra part, this expectation will generate a matrix. Okay, and this matrix will be in this way. So it will be the expected value of x1 minus mu1 square. Okay, and here will be expected value of x1 minus mu1 times x2 minus mu2, and so on until expected value of x1 minus mu1 times xn minus mun. Okay, and then we go in the same way, and you can see the diagonal of this matrix contains the variance of every random variable here. So here will be sigma 1 square, sigma 2 square, sigma 3 square, till sigma n square. The values here are the covariance between the different random variables. So if all these random variables are independent, then all of diagonal elements, the other elements here, will be 0, and only we have the diagonal elements which contains the variance of every random variable. Okay, this is called the covariance matrix. Usually it is written as R, actually, RXX. So this is called the covariance matrix. Covariance matrix is one of the most important functions or matrices in probability theory in general, and mainly in linear in machine learning. Okay, and actually based on this covariance matrix, we can now define the multivariate normal distribution. The multivariate normal distribution, it could be defined as f of x bold. X bold means that we have x vector now with n different random variables. So we have x1, x2 up to xn. Everyone is continuous now. We talk about continuous case. Okay, this equal to 1 divided by 2 by, okay, of the power of n divided by 2 times the determinant of the covariance matrix of the power of half, okay, times the exponent of minus half x minus mu x transpose times the inverse of the covariance matrix that it was explained before times x minus mu x. Okay, so you can see this value actually, because as we said x is column vector, so this vector will be, the dimension will be 1 by n. Rxx is the covariance matrix and we take the inverse, but the dimension is n by n. And finally the dimension of x minus mu x is n by 1. So making this multiplication, you will get finally scalar value 1 by 1. So this will be a scalar value. And this is the determinant, and we know that the determinant of Rxx, or for any matrix, this of course should be square matrix, and the determinant is a scalar as well. So you take the square root of that scalar value. Okay, and this will be positive always, because Rxx actually is always symmetric function. Or symmetric matrix, sorry. Rxx is always symmetric matrix, which means that its determinant is always like positive value. Okay, so this is generally the multivariate normal distribution. Multivariate or normal distribution is one of the bases in machine learning. Because it is valid in many different applications to assume that the distribution of data that we have is is multivariate normal distribution. So X actually, it can be like your data set. Okay, and in general we represent such kind of distribution like X. It is represented like normal distribution with size n. So just to distinguish between this n as a number of the random variable and n as normal distribution, we can use n small. of mu x is a vector of the mean, and also r x x, which is the covariance matrix. The covariance matrix is important to remember what is the meaning of the covariance matrix. Actually, we can also compute the correlation factor between any two random variable. So we call them like correlation between any two random variable like xi and xj. It can be easily computed from the correlation matrix or covariance matrix as the covariance between those two random variable xi and xj divided by the standard deviation multiplication of each one of them. So it is sigma I times sigma of xj. Okay, so this gives us the correlation factor. So this correlation or the between two random variables. As we said that if they are not correlated or independent, then the covariance is zero. So the correlation will be zero in case that there is independent. Okay, in case of dependency, then we can look to this correlation factor, that if it is positive toward 1, then the correlation is positive, which means that as x1 or as xi increases, xj also will increase. So there is a relation between them in direction of the positive. And if the result was in negative size, in negative side, okay, which means that they are like correlated but in negative way. So it means that when xi increases, usually xj decreases, or the reverse. So they are not going in the same direction. So the correlation is negative. For example, if we are looking to the relation between like age or between, for example, certain disease and, for example, the body weight. Okay, so we can see that if they are related or not by looking to this correlation factor. Correlation gives us if it is positive, which means that those who are overweight, usually they have more the possibility to get that disease. Or, for example, for that who are smokers, okay, that if they have some certain also disease based on if they are smoking or not, or between the number of cigarettes they are smoking and how likely that they will get that problem, or and so on. So this could be done or could be observed by looking to the correlation factor. And this is actually well known in statistics in general. Yes. What if, in case that, of course, as we said, if those random variables are independent, then we will have the covariance matrix will be diagonal matrix only, as we said, and the diagonal elements will be the variance of these for each random variable. Okay. Okay, and now I think we have done with the general review of probability theory. And just maybe the last thing that I want to mention, in case of random process, a random process like in time series case where we have things changing with time, like for example the stock price. So the stock price is random, but also it is function in time. So in that case, we have a random process, not random variable. Okay, so if we assume that every day is an event, and this is the stock market, like day by day, like 24 hours, and every day we assume that it is an event. So this is event 1, event 2, event 2 of course can be different, and so on. So in that case, we can see that if we take any at any time, we can define that x, but it will be function in the event itself a and time t. So a is the process, is the event, for example day 1, day 2, and so on. So and t is the time, or the event can be like different countries, for example the stock market in different countries, and so on. In this case, if we want to compute the average of the any random variable, for example, for the certain random variable, if we take the average, for example, of x, we need to define at what time, at what time, for example, at certain tk, for example, then this expected value of x at tk. Okay, which means that it will give me the integration as we did before. So x and times the distribution, but the distribution itself, actually it becomes now function in t, okay, of x dx. However, that we take the integration with respect to the random process itself, but we have to take into account the time t in the distribution, and this will generate like mu x, but it will be function in time, in the time. So now it will be function in time. So the mean now is function in time. Like if we talk about the average of temperature per month. So actually, when we talk about the average of the temperature is not the same. It will like fluctuate from month to month. Like it is different in the winter than in the spring, in summer. So it will be function in time. Of course, you can take the overall mean, but this might hide some important information about the fluctuations with time. Okay, and now we should also define a new thing which is called the correlation. The correlation of random variable x, it is defined as the correlation of this random variable between two different time. For example, t1 and t2. T1 and T2 is defined as the integration of xt, okay, at x at T1 times x at T2 times the distribution between x at T1, x at T2, x at T1 and T2, or we can put just x and we put t, okay, dx at T1 and dx at T2. So this called the correlation in general between T1 and T2. Actually, this is equivalent to the variance in case of random variable. But now we have to take into account that the time. However, if you put Rx at the same time, for example, T1 and T1, it means that this will be x squared and times f of x dx. So this will be that like the expected value of x squared in case of random variable, not random process. Okay. However, remember that this will be equivalent to variance in case of zero mean. In case of zero mean, but in general, what is equivalent to the variance is known as covariance, auto covariance. The auto covariance, yes, is defined as cxx, but now we put t1 and t2, and this will be the expected value of x at t1 minus the average at x at t1, which means that actually it is mu at t1, okay, then multiplied by x at t2 minus the expected value of x at t2, okay, and this of course equal to the correlation, autocorrelation function between t1 and t2 minus the mean at t1 multiplied by the mean at t2. Okay, so this is generally for a random process. Now we can define or we can simplify this one for the case of a stationary process. A stationary process means that the random process, it doesn't mean at what time you take the average. So the average, the expected value of x at any time t for any time, this will be mu x. So you can see that the mean is not function in time. So this simplification actually like simplify the analysis of random processes, and also the autocorrelation between any times t1 and t2 is the same as the autocorrelation of t2 minus t1. It is not depending where you take the t1 and t2, but it depends only on the time difference between t1 and t2. This will be correct in case of stationary process. in case of a stationary process. We can also simplify it further for the ergodic process. Ergodic process is the process where the mean is, you can find the mean by just looking for one time realization. For example, as we said for the stock market, this is for certain day, another day, for example, and so on. So they said that if you take only one time realization and you average over it, so expected value of x actually equal to the 1 over t, the integration from minus t over 2 up to t over 2. Now you can see that we talk about x of t dt, okay? And actually this, when the limit, I have to add one thing here. Yes, so this is x, the expected value of x equal to limit when t goes to infinity. So when we take very long time or very large time, okay, and then we take the average, so the time average is the same as the ensemble average, so it will be like mu x. This is very strong assumption actually in many applications. For example, if you take the average of January, the average of the temperature in January or in February, and you say that this average is the same as for every month. Of course, it is a strong assumption. However, in some applications, it can be accepted, but not always. Okay, the same for the for the correlation, the autocorrelation function R x of tau. This is the time difference. They say that it is the same, that limit when t goes to infinity, 1 over t, and the integration you take from like from minus t over 2 to t over 2, and then you multiply this x of t, okay, times x of t plus or minus tau, then dt. Okay, so when you take the average with the difference tau, okay, then we say that this is the autocorrelation function, and the assumption that this autocorrelation is the same as the ensemble autocorrelation is also strong assumption, but it is applicable in some applications, especially when we deal with stochastic random or stochastic differential equation. Actually, we need to have some like strong assumptions to be able to solve some problems. Okay, so this is called ergodic process, and you remember that the process that we have general, the non-stationary process. Under it, as a special case, we can have a stationary process. Under it, as a special case, we can have ergodic process. So ergodic process is very strong assumption for random processes in general. Okay, that is all we try in these two sessions, about 2.5 hours. We try to like conclude many things related to probability theory and the stochastic process. There are some other like material will be added, so you can also follow the other materials in order to understand more and to see some like examples related to that. Thank you very much.